Now that we've gone over ascending tracts, I've decided to make a separate video for descending tracts. So ascending was you're thinking sensory information. Think it's going from the periphery to the cord, and then it has to ascend or go up to the brain for full integration. Now descending is going down. So we're thinking motor stuff, because motor stuff begins in the brain and then it has to go down the cord and out to affect whatever muscle or organ that it's affecting. So hopefully it makes sense then. If we're looking at the words themselves of the tracts, it's going to start in a higher center like the cortex or the brainstem, and it's going to end in the cord. So it's going to be something spinal when you're looking at the words. So the first one we'll learn about is corticospinal. We're going to learn about vestibulospinal, tectospinal, reticulospinal. So just breaking down the word gives away that it's a descending tract, or it's going to have motor function because it's starting up high and it's ending in the cord. They all end with spinal. Whereas with ascending tracts, hopefully you're recognizing that those the word started with spinal, like spinocerebellar. So you can break down from there that it's going to be sensory because it's going up the cord. It's going from the cord to the brain. So our first descending tracts are our corticospinals, and I flipped to page 78 first because I just want to show you down on the cross section of the cord where those are. So we have the anterior corticospinal and the anterior funiculus. If you can look down at the bottom right, it's very small, and I have it labeled there. On the left side of that diagram, the lateral corticospinal is that huge labeled one. It's in the lateral funiculus. So here again, we're seeing the two tracts named for where they are in the cord, named for the funiculus they're in. And if you flip to page 77, when we go down these lines of information here, the anterior corticospinal only has about 5 to 15% of the total corticospinal fibers. Whereas if you look on the other side of the page, the lateral corticospinal has 85 to 95% total of the fibers of this pair. So the lateral corticospinal are the ones that we are mainly going to be concerned with because they are you'll see the function is the more important function, and they take up the most of the fibers for these tracts. So know the numbers, 85 to 95%. And then I'm keeping this slide up just to hopefully help you put that together, because when you look at the diagram of the transection of the cord and you see the lateral corticospinal labeled in red there, it's literally the biggest labeled tract of the descending tracts on the diagram. So for me, when I'm looking at the diagram and I see that huge one labeled, I'm like, okay, it makes sense that that is the one that's going to have most of the fibers. So that's the one that we are mainly concerned with. We do have to know the information with the anterior, but for this class and for the rest of your time at Palmer, you're going to be hearing a lot about the lateral corticospinal tract. So now we're going to come back to this page, and we talked about the first two in this little flow chart. The next set of information down talks about where they cross. So anterior, most are going to cross in the spinal cord, whereas with the lateral corticospinals, they're going to be crossing in the pyramids of the medulla oblongata. So lateral corticospinal, the one that we are mostly concerned with, crosses in the brainstem and the pyramids of the medulla oblongata. You absolutely need to know this. We're going to talk about it a lot more before we finish this exam material, but realize it's different from the anterior. Those are crossing in the cord, so they're crossing in two different places. I have circled and starred on my page up on the slide because you do need to know it. And when we talk about pyramidal versus extrapyramidal tracts, this lateral corticospinal tract is our main example of a pyramidal neuron. So when you see the word pyramidal, I want you to think lateral corticospinal and then connect, well, why am I thinking that? Well, the lateral corticospinal tracts are crossing in the pyramids of the medulla oblongata. So still sticking with lateral corticospinal, I'm going to skip down to the last part right here. What is its function? So lateral corticospinal tract is critical for initiating and accomplishing precise, skilled, voluntary muscle movements, especially in the distal extremities. I recommend just reading that out loud. It's kind of like with the dorsal columns, 2-point touch, kinesthetic, vibratory sensation. You say it so many times that it just kind of comes out. But that's what you need to do with this lateral corticospinal tract. You need to know it is initiating precise, skilled, voluntary movements, especially in the distal extremities. And if you break down that phrase, it makes sense. If you're thinking hands and feet, I use hands as a good example because what do your hands do? They do precise and skilled movements. So knowing that this lateral corticospinal tract initiates precise, skilled, voluntary movements of the distal extremities, I'm going to jump back one to where it says it runs the entire length of the spinal cord. So once I know the function, it's reaching, this lateral corticospinal tract is reaching all the way down to the feet and all the way to the hands. Then I tell myself, okay, well, that makes sense that it's going to run the entire length of the spinal cord because it has to reach everywhere in the body. And the reason I explain it to myself this way is because it helps me remember when I come to the anterior corticospinal tract on the left side of this page, it only terminates by the mid-thoracic cord level. So then I think, well, why does it only terminate to the mid-thoracic cord level? And that's because, or at least this is how I explain it to myself to remember, I go down and it says function unclear. They seem to influence axial musculature of the neck and shoulders. So then I'm like, okay, well, if it's the function's unclear and it might influence the neck and shoulders. So I'm like, okay, well, that makes sense why it would terminate mid-thoracic cord level because it doesn't say the function goes all the way down to the hips, knees, or feet. So that's how I remember that anterior corticospinal tract terminates by mid-thoracic level. That kind of goes hand in hand with its function of maybe influencing the neck and shoulders, the axial musculature there. To build off that one more time, to remember the difference between anterior and lateral corticospinal, I kind of think of it as like anterior corticospinal is like the portion of the corticospinals because going down the line, the lateral corticospinals are very important. They're initiating precise, skilled, voluntary movements of distal extremities. It runs the entire length of the cord. It's our main pyramidal neurons. Good example of that. And they take up most of the fibers of the corticospinals, 85 to 95%. Whereas anterior corticospinal, I'm like, because it only has 5 to 15% of total fibers. The function is unclear, and it doesn't even go the whole length of the cord. It terminates by mid-thoracic level. So I kind of use that theme of like, it's like an tract. Is that true? Probably not, but that's what helps me remember that anterior is the smaller one, terminates earlier, and the function's unclear. Whereas again, lateral is like super important. And I know I mentioned it, but I'm just going to say it one more time. The big word I want you to focus on here is initiating for lateral corticospinal. It's initiating precise, skilled, voluntary movements because if you break down the word corticospinal, so it's going from the cortex to the spinal cord. So this neuron or neurons in this tract aren't actually reaching the hands or feet. They synapse on the neurons that then go out and innervate. So they don't innervate, they initiate. We'll talk about that more in the next few slides. But big word, initiate rather than innervate. A couple things I want to talk about on this page still. So on page 79, a lot of the stuff I'll talk about is outlined on there. So make sure you mark that stuff in your book to make sure you know, but I have most of it on this page. So I'm going to go through it here. At the top right, I have in purple next to a star, one neuron start to finish. And if you turn the page to 79, it's got a letter C is where this information is. So these are the only axons or fibers that begin in the cerebral cortex and run uninterrupted to the spinal cord. So there's no synapsing, They go right from that high brain center, the motor cortex, all the way down to the cord. So it's going pretty much from the highest up you can get in the brain to the bottom of the CNS. The other descending tracks we talk about, yes, they'll be uninterrupted, but they're not starting in the cortex. They'll all be starting in the brainstem area. So make sure you know that these are the only tracks, one neuron start to finish. And then another big thing that you're going to want to make sure you know, and I wrote it at the bottom of this page, it's on page 79 as well, but I recommend you write it on this diagram so you have it all in one place when you're studying. The cortical spinals, so it goes from the cortex to the spinal cord, just breaking down the word, cortical spinal. But where is it synapsing? So it's going to be synapsing on rexid lamina 7. If you can remember rexid lamina 7, we talked about on that page in the book, many descending tract fibers synapse with neurons in this lamina, and the example was cortical spinals. So that's where we're seeing that. So the cortical spinals are synapsing on rexid lamina 7, but then those go to rexid lamina 9. So how I remember that it goes from 7 to 9 is I just think of it as, in terms of counting, the number 7 comes first, and then 9 is the next odd number after that. So that's how I remember that it goes from 7 to 9. So majority synapse in 7, communicate with 9, but then there's a specific type of neurons, or fibers I should say, that go directly to 9. So they bypass 7 and go to 9, and those are called Betz cells, and I have it written up there. It's on the next page. They're also called giant pyramidal cells. So no, giant pyramidal and Betz cells are the same thing. And there's a percentage on the next page too. It's 3%, or it says probably less than 3% of the lateral corticospinal axons terminate directly on lamina 9. So they bypass 7 and go right to 9. No, they're called Betz cells. No, it's about 3%, and know that those are specifically lateral cortical. So just kind of tying it together, what we know about the rexid lamina, remember we said the posterior horn was going to be mostly sensory stuff, and the anterior horn is mostly motor stuff. So if you think about it, when we were studying all the ascending tracks, we said those were associated with rexid lamina 2, 3, 4 when we're talking about the spinal thalamic. So those are the posterior horn rexid lamina. Those deal with sensory, ascending tract synapse there. Now we're talking about the corticospinal, which we know initiate skilled voluntary movement. So that's motor, descending. So hopefully it makes sense that they're going to synapse in these anterior horn rexid lamina, like rexid lamina 7, then 9. And to take it even further, if you can remember, the one big thing we said to know about rexid lamina 9 was that we had, it's the reason the ventral horn is called the somatic motor horn. We have those class A alpha motor neurons, the largest, fastest conducting motor neurons in our bodies in rexid lamina 9. So hopefully that, going through all that, it makes sense and you can kind of tie it all together that way. One last thing I want to mention on this page, while I have it up because it's labeled, I think we're going to get into this on the next page. I have it labeled at the top pyramidal, so we know our lateral corticospinal tracts are our big example of our pyramidals. And then I have circled extrapyramidal start here. So the reason I have that on this page is just to show you when we get into pyramidal versus extrapyramidal neurons, pyramidals are the ones that are starting in the cortex. So this, I think of it as like the super higher brain center is the cortex area, the cerebral cortex, whereas extrapyramidal is going to be starting in the brainstem area. So pyramidal's up top, and then extrapyramidal is a little further down in the brain, such as the brainstem. So keep that in mind before we start talking about that stuff. Now we're going to get into lower motor neurons versus upper motor neurons. So the next couple pages are very important for you guys to know. If you have any questions, make sure you ask, because this stuff is hit pretty hard on the exam. So I want to make sure you understand it. Lower motor neurons, I have the definitions up here on the slide, are neurons that originate in the cord or the brainstem and extend into the PNS to innervate somatic musculature. So we're not starting in a higher brain center. We're starting, I take the word lower from lower motor neuron, and I think we're starting lower down. So we're starting in the brainstem or the cord. So that's the CNS portion. And then it goes out into the PNS to innervate musculature. So these are the fibers that are actually innervating when you make voluntary muscle movements. They're the fibers that are firing to actually make that happen. So they start in the CNS and leave to the PNS. I've got up there, innervate is in red. And the reason I put it in red is because it's similar but very different to, if you look on the other side of the slide, upper motor neurons. It's a little different. I'll go through the examples in a second, but first let's go through the definition of upper motor neurons. So these are neurons from higher brain centers like the cortex or brainstem that influence the so-called lower motor neurons. So corticospinals are a good example of this. We said, taking the definition, neurons from higher brain centers like the cortex, and then corticospinal, obviously we know starts in the cortex, and it goes to the spinal cord. So these upper motor neurons are entirely in the CNS. They do not leave the CNS. Again, going back to our corticospinal example, it goes from the cortex to the spinal cord. So we know it's not leaving the CNS because both of those are in the CNS, the brain and the cord. That's different from lower motor neurons that we said they start in the CNS but leave the PNS. So what the upper motor neurons do and how I think of it is I think upper brain and cord is going to influence, so it's going to synapse on the lower motor neurons, which then leave the cord to innervate, or leave the brainstem to innervate. So upper motor neurons influence lower motor neurons, or they initiate the lower motor neurons to go do their thing. So examples of upper motor neurons is going to be anything that starts with cortico. So corticospinal is going to be our big example because that's the one that we specifically learn about in this class. But there are anything that starts with cortico and ends with something. That's why I have cortico something, cortico anything. That's going to be an example of an upper motor neuron. So when you break down the word, decide, does it stay in the CNS or does it leave the CNS? And that will tell you if it's an upper motor neuron. Coming back to the examples of lower motor neurons, those are going to be our class A alpha motor neurons. It's a good example of that. So let's talk about those. We said those were the largest, fastest conducting motor neurons, right? Those start in rexid lamina 9, and then they leave to innervate whatever muscles they're going to. So hopefully that makes sense. Breaking down the definition, they're starting in the CNS in rexid lamina 7. They're leaving to go innervate the musculature because they're the fastest, largest conducting motor neurons. So hopefully that makes sense. Another good distractor, or one that trips people up, is cranial nerves. And I just abbreviated to CN on my slide there. Cranial nerves are a great example of lower motor neurons. I think some people get confused because they read cranial nerve and they think like cranium, brain, so it has to be starting in a higher brain center. But the cranial nerves actually all have their origins in the brainstem, and the ones that have motor function leave the brainstem to go innervate the musculature. So a good example would be like any of the cranial nerves that innervate eye musculature. So they originate on the brainstem, but obviously they have to leave the brainstem to go innervate the eye musculature. So I think another reason students get tripped up is because it's so close to the brain, but it is actually leaving the CNS. Another good example, and you can write this down in your book, we're going to talk about it on the next page, I think, is our cranial nerve 11 is our spinal accessory nerve that starts in the brainstem, but it leaves because we'll talk about it's going to innervate the traps in the SCM. So starting in the CNS and the brainstem, leaving to innervate skeletal musculature. And the second half of the page goes over what it looks like clinically if you have an upper motor neuron or a lower motor neuron lesion. So I didn't put this up on my slide because I would have typed it to look exactly like how it looks in the book. So what I recommend doing is right above where it says, I'm looking at 4B in the book, and then it says UMN lesions. So right above that, I wrote upper equals increasing. So if you take the word upper, it means if you're going up, you're increasing, right? So that leads me to think when you have an upper motor neuron lesion, you're going to have an increase of reflexes, you're going to have increased muscle tone, and that goes right along with what it says, hyperreflexia, increased muscle tone. Whereas with lower, I wrote lower equals decreasing right above lower motor neuron lesion. So if he gives an example of a lower motor neuron lesion, I'm going to think it's going to show up clinically with decreased muscle tone, decreased reflexes. You can have areflexia or hyporeflexia. So everything is decreasing, atrophy. And if you think about it, a lower motor neuron is the one that is actually innervating the muscle tissue, causing it to contract. So if you have a lesion and it can't do that, it should make sense that the end organ or the somatic muscle is not going to be able to work, so it's going to atrophy, or you might not have your reflex because the nerve just straight up is not reaching the muscle. Whereas with the upper motor neuron lesion, that's the one that is initiating or influencing the lower motor neuron. So if you have a lesion with the upper motor neuron, it's not getting the information to the lower motor neuron to tell it what to do. So you can have the excess lower motor neuron activity causing the hyperreflexia, causing the increased muscle tone. And then with both, I kind of skipped over the first part. Hopefully it makes sense with either of these because we're dealing with motor neurons. You're going to have a reduction or absence of voluntary movement. No matter what, if you have a lesion in an upper motor neuron or lower motor neuron, it's going to affect voluntary movement. It's just whether it's going to be hyper or hypo. So those are that first line under the clinical signs is going to be the same. I'm hoping you guys are able to follow along without me putting this stuff up on the slides, but a couple other things with upper motor neurons and lower motor neuron lesions. We've got under upper motor neuron, we've got the words clonus and Babinski sign. So the big thing here to know is that these are signs of an upper motor neuron lesion. If you memorize that, great. I'm going to kind of talk about ways to remember it. So I would write down clonus, relax and contract, and then cogwheeling. So if you, usually in live classes, Dr. Torgerud will show what it looks like or kind of give an impersonation. So I would look it up on YouTube, and hopefully when you see it's a quick relaxing and contracting. So hopefully for you that resonates with a hyper reaction rather than a hypo, because we said hyper is with upper motor neuron lesion, upper increasing, and lower motor lesion is lower or decreasing. And then Babinski sign is a plantar reflex in babies that goes away. So with Babinski sign, you swipe the bottom of a baby's foot in a certain way, and it causes them to like hyperextend their toes. And that goes away, I think, within 2 years. But if you have an upper motor neuron lesion as an adult, it comes back. So if you study and you know what clonus and Babinski sign are, hopefully it makes sense that that is a sign of a upper motor neuron lesion. If you don't want to know about that, big thing is to know clonus and Babinski signs of upper motor neuron lesion. And then one thing that I think students get confused on is for the lower motor neuron lesions, we've got muscle fibrillations or fasciculations. It would seem like those are kind of like an upper or increasing sign, but those actually go with lower motor neuron lesions. So be able to, again, distinguish which ones go with which. This slide I just threw up. It's the bottom of page 80. It just shows, it's not a testable diagram, but it just shows how the upper motor neurons are what synapse on the lower motor neurons. So hopefully it's good visual for you to see that. Upper motor neurons do not leave the CNS. So you can see the two that start up top in the cortex area, and one goes to the brainstem, one goes down to the cord, but they do not leave the CNS. And then the lower motor neurons are the ones that start in the CNS but leave. So the examples that are there is cranial nerve 5 is an example of a lower motor neuron. I accidentally cut off it would go innervate the muscle, the lateral pterygoid, and then we can see on the second example, it's an upper motor neuron that goes down and synapses on the lower motor neuron, which is the femoral nerve. And then the femoral nerve is the lower motor neuron that actually goes out and innervates the muscle, the rectus femoris. All right, next page is 81. And this is where we're going, if you look at your book, over pyramidal versus extrapyramidal neurons. So I put up what we were talking about on page 80 with lower motor neurons and upper motor neurons, so you could visualize that both pyramidal and extrapyramidal are upper motor neurons. So now we're just dividing upper motor neurons even further. So starting with pyramidal neurons, there are upper motor neurons involved with initiation of skilled voluntary movements. Hopefully that phrase sounds really familiar because that is the function of the lateral corticospinal tract, initiation of skilled voluntary movements. Going back to lower motor neurons versus upper motor neurons real quick, I have in red, if you look on my slide, lower motor neurons were the ones that innervate, and then upper motor neurons were the ones that don't go out and actually innervate the muscle, but they influence or initiate. So now we're taking those two words, influence and initiate, and putting them to their correct subdivision. So pyramidal are the ones that initiate, and extrapyramidal are the ones that influence. So pyramidal, the big one you want to think about, again, are corticospinals. Remember, the lateral corticospinal is crossing or decussating in the pyramids of the medulla oblongata. So I'm sure by this point you guys know that I like to make things easy by taking what the word means or breaking things down. So when we look at extrapyramidal, if we compare that to pyramidal, the difference is the word extra. So I think extrapyramidal is going to be doing extra things to make the movement smooth, because we said pyramidal was initiation of skilled voluntary movements. Now extrapyramidal, I'm taking that word extra and saying, okay, that's going to be doing something extra besides initiating. So it's going to make the movement smooth and effective. And that's in the book, and I have it on the slide, it says, as a general rule, they influence posture, muscle tone, and enhance reflexes in order to make voluntary movements smooth and effective. So every time I read that extrapyramidal, again, repeating myself for like the 8th time, it's doing all the extra stuff to make movements smooth and effective. So that would be your posture, muscle tone, reflexes that they're influencing. So I put those words in red so you can differentiate between lower motor neuron, upper motor neuron, and then again between the two different kinds of upper motor neurons. One other thing I have in highlighted, pyramidal is going to be starting in the cortex, so even like the highest brain center. And then extrapyramidal is going to be starting a little bit lower down in the brainstem, but still in the CNS, right? Because they're both upper motor neurons. They do not leave the CNS. The next 3 tracks we're going to talk about are our examples of extrapyramidal neurons. So tectospinal, rubrospinal, and vestibulospinal I have right under extrapyramidal to show you that those are the examples of those. And when you break down those words, tectospinal, rubrospinal, it's giving away where in the brainstem the tract is starting. So first up, we have the tectospinal tract. This is still on page 81. As we go through, I'm going to put, by the end of this section, I'm going to have all of the extrapyramidal tracts next to each other so you can compare and contrast the origin, if they cross or not, where in the cord you can find them, and what their functions are. So that's what we're going through with the tectospinal tract right now. And then those are the things you need to know for the other two. So tectospinal tract has the origin in the superior colliculus of the midbrain's tectum. Yes, you need to know this. It's kind of a mouthful, but we don't learn about the midbrain till the third, I think, exam. So it's kind of memorization at this point. The fibers are going to cross as they descend, and they're terminating in the upper 4 cervical cord levels. So this is the upper motor neuron, and where it's terminating in the upper 4 cervical cord levels, that's the lower motor neuron it's terminating on, which is going to be the spinal accessory nerve or cranial nerve 11. And I'll go through the pathway of that in a second. Their function is they deal with reflexes, with sight and auditory stimuli. So they do this by influencing the trapezius and sternocleidomastoid. So this is a reflex. It says dealing with sight and auditory. So if something moves really fast on your left side, or there's a big loud bang on your left side, the reflex is that your opposite trap and SCM are going to contract to pull your head away from that loud stimulus that happened on the opposite side. So I put up an example of how the pathway would go if we're using the opposite side now. So an impulse on the right side happens, either a loud bang or a quick movement on your right. The right tectospinal tract is going to cross to the left. It crosses as it descends. It terminates in the upper 4 cervical cord levels because that's where the cell bodies of the spinal accessory nerve are. So it's synapsing on the left spinal accessory nerve. And then the left spinal accessory nerve innervates the left trap and FCM. So it causes those to contract to perform that reflex. We're about to talk about the next 2 extrapyramidal tracts, and those are found at all cord levels. So this is where knowing the function can kind of help you figure out where it is in the cord or not. Because if you know the tectospinal tract is only influencing those 2 muscles, the trap and SCM, why does the tract need to be found extending all the way down to the bottom of the cord? It doesn't, because it's only influencing those 2 muscles that are up by your neck. So that's how I think through that to kind of help me remember that this tectospinal tract is only going to the upper 4 cervical cord levels. All right, turning the page to 82. Now we're going over the rubrospinal, tract. So this is another extrapyramidal tract, starts in the brainstem. Specifically, it's going to have its origin in the nucleus ruber or red nucleus of the midbrain's tegmentum. Another mouthful, but you need to know it. So one thing I want to point out, and I put it in caps, is tegmentum and tectum are 2 different words. So the tectospinal tract starts in the tectum. The rubrospinal tract is the red nucleus of the tegmentum, both in the midbrain. The tectum and the tegmentum are both in the midbrain, but we don't study the midbrain, like I think I mentioned before, until the 3rd exam material. So the rubrospinal tract also crosses as it descends. This one is going to reach all cord levels. We said tectospinal only terminates in the upper 4 cervical cord levels. Rubrospinal tract is reaching all of the cord levels, which hopefully makes sense when we go through the function of it. So I have it on the slide and it's in your book. Predominantly influence. There's that word influence again, not initiate, but influencing hand and foot flexor musculature. So an easy way to remember this that I learned when I was in first try taking this class, our past tutor told us, if you think about what do, bros flex. So that's a fun, easy way to remember. If you remember rubrospinal, bros flex. So can help you jog your memory on rubrospinal is influencing flexor musculature, specifically hand and foot. So we're thinking distal again. And that's where I kind of connect, well, if you were going all the way to the hands and the feet, it makes sense to me that this tract is going to be present or reaching all cord levels. Another thing, if we were live in class, Dr. Torgard would probably do this, and I would probably do it as well, is have everyone flex your bicep and then say, okay, now activate your tricep and extend your arm while keeping your bicep flexed. And you can't do it, right? You can't flex your bicep and extend your tricep at the same time. That is referring to the second part of the purpose or the function of the rubrospinal tract. It's going to influence flexor musculature, but also inhibit extensors. So that should make sense. It's a pretty simple concept. You can't extend and flex at the same time. So then when we talk about the vestibulospinal tract next, which influences extensor musculature, the same thing goes for that. It influences extensors, but then is going to inhibit flexors. So they're kind of flipped and opposite. So moving down on the page and in my slide, we've got the function again. So I have contralateral bolded because remember this crosses. So the right rubrospinal tract is going to influence left hand and foot musculature. So I put an example of how this might look in a question under the rubrospinal section on my slide. Patient has a lesion on the right rubrospinal tract. What function is affected? So how I would work through this is I would read right rubrospinal tract, and I would say, first off, what is the function? Rubrospinal tract grows flex, so I'm looking for flexor musculature. So that rules out extensors. Yes, it says extensors are inhibited, but the main function here is going to be the flexor musculature, so that's why I'm going with that. And then from there, I have to decide between right and left. So I need to remember that the rubrospinal tract crosses, which is going to make it contralateral. If you remember contralateral hand and foot musculature, great. So then that leaves me with my answer, B, left flexor musculature. It could also say something like left hand flexor musculature or left foot flexor musculature. So just a quick example. One last thing to be aware of, it's the last sentence on page 82, and I've got it up on my slide as well. Rubrospinal tract assumes some of the function if corticospinal tract is injured. So remember, corticospinal tract is initiating and accomplishing precise skilled movements, voluntary movements in the distal extremities. So we know that the rubrospinal tract is also dealing with distal extremities. So hopefully that kind of makes sense that it's going to help out if the corticospinal tract is not working correctly. We'll talk about another tract that also helps out if the corticospinal tract isn't functioning, and it starts with R as well. It's the reticulospinal tract. So an easy way for me to remember that was just both tracts that start with R are going to help out when the corticospinal tract is not functioning. So we'll mention it again soon. Last of the extrapyramidal tracts is on page 82. This is the vestibulospinal tract. So another big phrase for the origin, it's the lateral part of the vestibular nucleus in the medulla oblongata. Up on my slide, I put medulla oblongata in purple because I wanted to bring to your guys' attention that it's the only one of the three that has an origin in the medulla oblongata. So you need to know that the tectospinal and rubrospinal tracts, I have them in like a dark red up there. Those both start in the midbrain. Vestibulospinal starts in the medulla oblongata. The vestibulospinal tracts do not cross as they descend. I put that in red to bring it to your attention because the other two do cross as they descend. So how I remembered this was both tracts that have an origin in the midbrain descend. The one that doesn't start in the midbrain does not descend. So it kind of goes nicely there. So with the rubrospinal, we just talked about how that is going to reach all cord levels and influence hand and foot flexor musculature. Now the vestibulospinal is the opposite of that. So it's going to influence extensor musculature. So it's just the opposite of the rubrospinal, which means if it's influencing extensor musculature, it's going to inhibit flexors. And I have up on my slide, I put in blue ipsilateral, just to reiterate that the fibers do not cross, so make sure you know the difference there. One last thing you need to know about the vestibulospinal tract is the last sentence, both in my slide and in the book on page 83. Maintains proper orientation in falling and enhances spinal reflex capability. So first, I think with the spinal reflex capability, all of the muscles on your back are going to be extensors, right? They help you extend your back. So if vestibulospinal is dealing with extensors, that's how I make sense of that portion of it. And then when it comes to proper orientation and falling, think about if you fall or if you trip or something, the first thing you're probably going to do is extend your arm out, right, to catch you. So that's how I connect the maintains proper orientation and falling to the vestibulospinal tract. But know that both of those go with vestibulospinal. So those are the 3 extrapyramidal tracts. I put them all on the same slide. So I'd recommend taking a screenshot of this so you can kind of compare and contrast the similarities and differences between them. All right, I'm bringing this slide back. So now that we've gone through lower motor neuron, upper motor neuron, pyramidal, extrapyramidal, and all of those examples, I want to go through some examples so you guys are 100% sure of labeling different tracts. So the first one I have, it's in purple on the left side. So I have A through E, and then choose all that apply. So think about the tract gracilis. What can it be categorized under? Okay, hopefully you got the answer E and A, not applicable. So when I'm going through this, the first thing I think is, well, A through D is all motor stuff, right? It's descending. That's the section that we're on. And upper motor neuron, lower motor neuron, it literally has the word motor in it. And we know that pyramidal and extrapyramidal are subdivisions of upper motor neurons. So when I see gracilis, the first thing I think anytime I see a tract is, what is its function? Gracilis is ground up, 2-point touch, kinesthetic sensation, vibratory sensation. So it's sensory, it's ascending, right? So it would be non-applicable because we're not dealing with motor descending stuff with this tract, it's ascending. So hopefully that makes sense. Next one is lateral cortical spinal. I'm going to give it a few seconds and then I'll put the answer up. So pause it if you need to. Hopefully you got A and C here. So it's an upper motor neuron and a pyramidal. I have said multiple times throughout this video, every time you see lateral cortical spinal, I want you to think pyramidal, right? Because the fibers cross in the pyramids of the medulla oblongata. It's our big example of pyramidal neurons. A rule of thumb for this exercise here, if you ever pick C or D, if you ever pick pyramidal or extrapyramidal, then you have to pick UMN or upper motor neuron as well, because pyramidal and extrapyramidal are just subdivisions of upper motor neurons, which is why I left this slide up with the chart so you can kind of visualize that pyramidal and extrapyramidal both fall under upper motor neurons. So if you pick C or D, you have to pick A. Next one is rubrospinal tract. So I'll give you a few seconds on this one to decide which apply to it. The answer to this one is going to be A and D. Right off the bat, when I read rubrospinal, I think I know that's one of the 3 extrapyramidal tracts we learned. So it might be helpful to memorize tecto, rubro, vestibulospinal are the 3 extrapyramidal. And then, like I said before, if you pick pyramidal or extrapyramidal, you have to pick upper motor neuron. So that's how I thought through that one. If you want to take the long route, you can think rubrospinal, think of the function. It influences flexor musculature, so it's influencing. It's an extrapyramidal, and then from there, it's also a upper motor neuron. If you get confused on upper motor versus lower motor, think about, break the word down. So rubrospinal, so it's starting in nucleus rubra of the midbrain. It's ending in the cord, so it's not leaving the CNS. So the last page of spinal tracts, almost to the end here, we've got reticulospinal tracts. There's a medial and a lateral, and I have the transection of the cord up so you can see where they're at. By looking at the diagram, you can tell that they are named in relationship to each other because one is more medial, one is more lateral. Also, by looking at the diagram, it should make sense that the medial is in the anterior funiculus and the lateral is going to be in the lateral funiculus. So that is just by knowing the diagram, it's going to help you with that. The medial reticulospinal originates in the pons, and the lateral originates in the medulla oblongata. So how I remember, what helped me remember this is I have written up on at the top of my page that M's do not go together. So when I was studying, I was like, oh, wouldn't it be nice if the medial originated in the medulla because they both start with M? But that's not how it works. So by writing that out and looking at that when I was studying helped me remember that the medial, also known as the pontine reticulospinal, originates in the pons, and the lateral reticulospinal is going to be the one that originates in the medulla oblongata. Both of these are uncrossed, and they both have the same function. So that's kind of nice. Up until now, we talk about ascending tracts and all the sensory information that goes up to the brain to get processed. We've talked about all the voluntary motor stuff, initiating and influencing motor stuff, and now, so that leaves us with what we haven't talked about is autonomic function. So that's what these reticulospinal tracts are doing. So I circled in red, they have the same function. They're dealing with heart, blood pressure, respiratory rates. So when you think reticulospinal, think autonomic, think things that keep you alive, awake, your vitals. So it's organ stuff. We haven't talked about that yet. So we've got the origin down. Medial is originating in the pons and lateral is in the medulla oblongata. And they're going to terminate, they have the same area that they terminate in the medial parts of the ventral horn, or the word you need to know, intermedial lateral cells. Those are the IML cells we studied with Rexid lamina 7, if you can remember that. So I wrote it out on my book. I suggest writing it on yours too. And if you flip back to that section of Rexid lamina, it has all of that information about the autonomic preganglionic neurons that begin in that Rexid lamina. So these reticulospinal tracts are going down to synapse in either the sympathetic preganglionic neuron or the parasympathetic preganglionic neuron. And then those will go out to their respective organs and have their effect either fight or flight or rest and digest. I've also got circled. Again, we're seeing it may also serve as an alternative pathway if the corticospinal tract fibers are destroyed. So going again back to how I mentioned both of the tracts that start with R that we learned about are going to help out if the corticospinal tracts aren't functioning. So I just remembered, if you remember the R tracts are the ones that help, then that's a pretty easy way to keep that in line in your head. Next, we've got fasciculus proprius, or propriospinal system, or under that it says spinospinal fibers. So make sure you know all of those words mean the same thing. Going off of spinospinal fibers, so it's starting in the spine and it's ending in the spinal cord. So hopefully it makes sense then. Going to number 2, it says fibers usually extend short distances up or down the cord. So you need to know that, and I think just knowing the word spinospinal fibers helps with that. The function is it's vastly important for coordination of spinal reflexes. So again, if these are starting and ending in the spine, hopefully it makes sense that they're important for coordination of spinal reflexes. So the theme here is spine, spine, spine. Another thing that's under 4 in your book, I have it highlighted. They are the first fibers to be myelinated in the fetus. So make sure you know that. And a way that I remember that is when I was studying, I would say fasciculus proprius, first fibers in the fetus. So I like all those F's that go together. I would just repeat that out loud a few times, and that helped me remember that. So spinal reflexes, fasciculus proprius, first fibers myelinated in the fetus. So I would just say that out loud a few times. Last tract, we have the dorsolateral tract of Lissauer. That should hopefully sound familiar from when you were studying Rexid lamina. We said that its synapses in lamina 2 are the substantia gelatinosa, so I ended up writing substantia gelatinosa under on my page just to kind of jog my memory there. other than that, be familiar with the rexid lamina it's in and then know its position. So it's between rexid lamina 1 and the posterior lateral sulcus of the cord. So if you read that and look at the transection of the cord, I kind of made a mark where rexid lamina 1 would be in purple, and it's right behind that. So it makes sense that it's posterior to that. And it sits right between the posterior column, that gracilis and cunatus, and the lateral funiculus. So just reading along that line and looking at the diagram, I think it makes good sense. So those are really the two big things to know about the dorsolateral tract of Lissauer. I also wrote in black on mine, lateral spinothalamic 2 at the bottom there. That's just to, again, as a review, that the lateral spinothalamic tract is the one that synapses in rexid lamina 2 as well. So those are the two that deal with 2. And that wraps up the tracts. So I'm going to skip to, let's see, page 86. What can cause a CNS lesion? If you don't have anything written there, I would just write trauma. I'm sure at this point, it was always a joke when I was in first try that you learn trauma is like a reason for everything. So if you don't have an example there, I'd just write trauma. There's other things like infection, tumor, but I wouldn't worry about that too much. Number 2 says upper verse motor lesions. We talked about all of that stuff already, so I'm not going to go over that again. 3 is just showing, it kind of goes over the concepts we talked about already with, think about the functions that happen in the dorsal horn. You're probably going to think sensory. Ventral horn is probably motor. Lateral is autonomic. So those are kind of general concepts. I'm not going to go through all of those. So I'm going to flip to page 87. So total transection of the spinal cord, there's some information under that, but I'm going to skip down to number 5, Brown-Séquard syndrome. So know what this is. It is total loss of either the right or left side of the spinal cord. So it's also known as a hemisection. So this is important because, and it says under B, could you describe the symptoms for such a syndrome at cord level, blah, blah, blah. So this is how we could ask a question on an exam rather than saying, I've kind of been giving examples throughout this exam material, but rather than saying somebody has a lesion in this tract, he could say a patient has a hemisection on the left and then ask a question based on that, and you'd have to put the pieces together. So that's how that one goes. And then we have a couple other clinical things going on. So tabes dorsalis is when bacterial tertiary syphilis, it gets to the tertiary stage and it results in the wasting of the dorsal funiculus. So I italicized dorsal, wasting of dorsal funiculus, to hopefully help you put together tabes dorsalis is the wasting of the dorsal funiculus. So, and remember, the only 2 tracts we have in the dorsal funiculus are gracilis and cunatus, but this one is going to be primarily affecting gracilis, so know that. And then I have the question, someone with this would lose what function? Because we're learning about what tabes dorsalis is, but the point of it is to know how it's going to affect the patient. So hopefully you were thinking vibration, kinesthetic, proprioception, 2-point touch, and then I added of the lower extremity or feet because that is what is primarily affected with tabes dorsalis. Next we have multiple sclerosis. So this hopefully you recognize it because we studied it for exam 1 stuff. It's the destruction of the CNS myelin, so don't forget that. And I have IO there, that's representing interfascicular oligodendrocytes, so don't forget about that. You're going to want to know, I put the characteristics under there. It's more common in females, and age of onset is usually between 20 and 40. Symptoms remit and relapse, so they kind of come and go. Amyotrophic lateral sclerosis is destruction of upper motor neurons and lower motor neurons, principally the lateral corticospinal tract. So what helped me study was I highlighted amyotrophic lateral sclerosis, and it mostly affects the lateral corticospinal tract. So that's what helped me remember that. And then knowing that, hopefully you're connecting, well, lateral corticospinal tract is an upper motor neuron, so that makes sense then. Males are afflicted twice as often as females. So for me, when I was studying this, I remembered multiple sclerosis is in women. So then I was like, well, ALS is going to be males. So one is one and one is the other. Another thing that helped me remember ALS is males is Stephen Hawking had ALS, sorry. So he's male, and yeah, just made that connection. It was an easy way to remember it. All right, everyone, that wraps up the spinal cord unit. So I'm not going to go through pages 88 and 89. If you have time at the end, I suggest going through it then, but I would focus your time and energy studying on the stuff that we covered and emphasized in these videos. So we covered a lot of stuff. If you have any questions, let me know. There's still quite a bit more to go through, so try to stay on top of everything, and good luck studying.